All right. Welcome everyone to the session on lower bounds. We have 5 great lower bound papers, and the first paper studies the foundational question of the communication complexity of fine-grained key agreement in the random oracle model, and Guangzhou Yang is going to give the talk.
Hello everyone, I'm Guangxu Yang. This is my first time to attend a conference, so I'm honored to be here. Today, I'm going to talk about the communication neural bonds of chain agreement protocol via density increment arguments. This is a joint work with Min Huang, Xin Yumao, and Jiapeng Zhang. We are from University of Southern California. First, I introduce the definition of chain agreement protocol in random oracle model. That is, there are 2 players, Alice and Bob. They share a random oracle, and they can do some queries to random oracle and communications. After communications, Alice output king A, Bob output king B. For correctness, we hope that king A equal to king B with high probability. And there is a third player called attacker. He can see the communication transcripts and query the random oracle. For security, we hope that any attacker see the communication transcripts and make a few queries counter guess the key. So here is a simple protocol called Moco-Pado as an example. In Moco-Pado, Alice uniformly sample x1 to xl and query the oracle to get fx1 to fxl. And Bob also uniformly sample y1 to yl and query the oracle to get fy1 to fyl. After they query the oracle, Alice just send the oracle answer to Bob, and Bob will check if there is I such that fyj equal to fxi, and send the fyj to Alice. At the end of communication, Alice output king A is xi, king B is yj. So for correct this, if we set n equal to 10 times L squared, then Alice and Bob will have common queries with high probability by Butler paradox. And if M is large enough, then K equal to K B with high probability. For security, since the attacker can only send communication transcripts, so giving a FYJ, he should make at least omega L squared queries to find X such that Fx equal to Fyj. In fact, recent paper proposed a variant of Moco-Pado achieve perfect combinations and the same security. Perfect combinations means that king A equal to king B with probability 1. So Moco-Pado only prevent a quadratic gap between the efficiency of the horned party and the attacker. So the question is, can we do better? Here is some negative results. The first result shows that any chain agreement protocol where Alice and Bob make L queries can be broken by the attacker with L to the power of 6 queries. There is a technique called intersection query, similar to Alice and Bob to do some queries. And this result improved to L squared queries. And this result implies that Moco-Pado is optimal with respect to the query complexity of the attacker. And they use a technique called heavy query. Intuitively, heavy query is that the attacker query the positions which queried by any Bob with high probability based on his knowledge. So heavy query has wide applications in different areas and focus on black box separation and the power of random oracle in a secure 2-party computations. So private results don't consider the communication conversation between Alice and Bob. And as we know, the amount of communication bits between Alice and Bob is also important in practice. For example, if we consider Moco-Pado, Alice and Bob need to exchange omega L bits. So the question is, can we do better with the same security and this communication? Here is a conjecture by recent people. They conjecture that any L query and C-bit communication agreement protocol can be broken by the attacker with CL queries. This conjecture means that Moco-Pado is also optimal with respect to communication complexity. So non-adaptive means that any Bob query is fully determined by their internal randomness. So as a partial result, they also prove the two-round case. That is, any SQL query and CB communication grammar long-derivative two-round protocol can be broken by the attacker with CL queries. And they also use the technique called heavy query and analyze the communication cost via a log technique. And analyze the communication cost means that to bound the number of heavy queries. So let's turn to our contribution. Our contribution, we prove the conjecture for perfect companies. Perfect companies means that king equal to king with probability 1. So our result implies that the protocol in written paper is optimal. Compared to previous technique, we also have some technical contribution. First, we propose credited queries. Intuitive related queries are not only heavy, since we consider the communication cost, so we should consider the query also credit credited communication transcripts. So we analyze the communication cost via a simple technique called density increment argument. This means we can bound the number of credited queries by a density increment argument. Let's turn to definition of credited queries. Credited queries means that we see the S is correlated, means that the FS the condition randomness IRB and the private queries giving the transcript the literal loss is large. So based on credited queries, we propose an algorithm for the attacker. The attacker is very simple. Just query the credited queries until with set L and until low credited queries, and update their knowledge after each credited queries. And at the end of algorithm, they output the majority of what possible output. So given this algorithm, we have 2 steps to finish our theory. The first step is we need to show that the algorithm will succeed with high probability. The second is that we should bound the number of iterations by communication complexity. We finish it by a technique called density increment arguments. Density increment argument is a powerful technique in combinatorics, but I think it's little known in cryptography. So density increment argument defines a density function to record the change of the view. So we prove this number, the expectation number of iteration of the algorithm is bounded by communication complexity. So first we review that at the beginning, the density function is phi tau implicit and is updated after queries. By chain rule, we show that the density function decreases at least epsilon in the expectation after epsilon queries in each iteration. And we also notice that the density function is always non-negative, since F is uniform distribution if we only condition on randomness and private queries. So combine the two factors, we will have that the expectation number of iterations you give a transcript is phi tau implicit over epsilon. And if we take expectation over the transcript, we will give our results. So here is a summary on our proof outline. The proof outline is as follows. First, we give an algorithm that the attacker query the created queries in each iteration and output the majority of what possible output. And the number one is that we bound this number of iteration is communication complexity. This is proved by density argument. And number two is that we show that the success probability of the algorithm is large. This is proved by rectangle view in communication complexity. So we omitted the proof in this talk. So last, I discuss some open problems. I think the first open problem is how to extend our perfect companies to imperfect companies. For our technique, we can't fix the transcript. We should consider the communication round by round to achieve imperfect companies. And another question is how to achieve adaptive protocols. And for this open problem, we have no idea right now. And the last open problem is that since heavy query has wide applications, so that's the open problem is that whether our created queries also have applications with respect to communication complexity. So that's all. Thank you.
questions? Maybe one question. Can you explain where you use the perfect completeness assumption in your proof?
We use it in a rectangle view. So our results really we should analyze the transcript rather. Another transcript is respond to a left rectangle, and we found some structure in left rectangle based on the perfect completeness property. So if you want to consider imperfect completeness, you should do it round by round, not fix the transcript.
Well, thank you. More questions? All right, if not, then let's thank Guangzhou again.
Okay.
All right, so the next talk studies the foundational question of the difference between the security of sponge hash functions and Merkle-Darmgraph hash functions in the preprocessing model, and Guangxi Duan is going to give the talk.
Thank you. My name is Xiaoqi Duan, and today I'm going to talk about the time-space trade-off for collision finding in sponge functions. So let's start with the domain extension hash functions. You should be familiar with this. That is, it is a hash function that will take a long message for input, and it will still come out with a very short hash value. That is to say, if we have an input, we can divide it into B blocks, say M1 to MB, and we can apply this function f on the first block of message M1, and we will get an intermediate value. And with this intermediate value, we can combine it with the second block M2 and apply the same function f again to get another different intermediate value. And we can repeat this for all the B blocks and finally get an output. So this is the domain extension hash functions, and there are many applications like the famous SHA-2. It uses the Merkle-Darmgraph hash functions. So in this setting, the function f can be seen as a random function. And another very famous setting is at SHA-3, they used sponge hash functions. And the different thing here is that in sponge hash functions, the function f can be viewed as random permutation because for efficiency reasons and practical reasons. So the difference here is that the adversary should also have access to f-1 because f is a random permutation, and also because this has been widely used in reality to have both access. And also, as usual, our target is that these functions it should be hard to find collisions with them. So maybe you will ask, because in SHA-3, there's an extra thing that we have the access to f-1. Is it possible that SHA-3 is somewhat less secure than SHA-2 in some sense? And the answer is somewhat yes in the following model. That is the so-called auxiliary input model. The intuition of this model is that what if in reality the adversary have some extra knowledge about the function used before? For example, if the function have some backdoors, he may use this information to design attacks more generally. So the setting of auxiliary input in model is that it is very similar to the random oracle model, except that the adversary will have the S-bit extra information about the function f. And with this information, he can also, as usual, make T queries to the f or f-1, and he will try to output the collision. And usually the trivial birthday attack also still applies because actually, you do not need extra information to perform a birthday attack. And in here, it is just T² over n or T² over r, where n and r are the function ranges in MD and sponge. But the interesting thing here is that except from this trivial attack, there do exist non-trivial attacks in this auxiliary input model. For example, we can look at the case for Merkle-Darmgraph that for different message lengths that indeed have some different known attacks. For example, when b equals to 1, you can see that there's a term of S over n, where S is the S-bit information that we have in the AI model. So it does is that in this auxiliary input models, there are more things that the adversary can get. And this is true for almost all parameters, like there's a new thing that performs better than the first day attack. And this is for the Merkle dam guard. And the interesting thing comes in sponge, that is, you can have a look at this fancy thing when b equals to 1. So what I generally want to say is that if you treat, say, C and R, they are of the same order as N, you will find that the advantage of this attack is strictly better than the attack for MD. So what does it mean? It means that because the adversary have the access to the inverse function in sponge, it means he can really take use of this advantage of the inverse function and to design a better attacks that will outperform the original attack in Merkle dam guard. I would like to mention that it's heavily utilized the inverse oracle, otherwise this attack won't occur. So as long as this situation occurs, it will be interesting to say what is exactly happening in auxiliary input model. For example, what about the security upper bounds? And there are many research in this area. Some of the earlier research will use techniques like presampling and compression, but most recently, the technique used are so-called multi-instance games. We will talk about it later. And what we want to know now is that with the help of multi-instance game, we indeed can have some nice results. For example, in the case of Merkle dam guard functions, we can prove almost tight bound for almost many parameter ranges, except that this when b is larger than 3 and smaller than t. And this is still open now, but the thing is that multi-instance technique, it works pretty well here for giving us this upper bounds in the AI model. But again, things become strange when we come to sponge. Actually, we actually do not have tight bounds for all the short collisions when b is smaller than t. So more specifically, these upper bounds, you can have a look, for example, when b equals to 2, in the current upper bound proved by multi-instance games, there's a strange, say, s squared t4 to the c squared term. This term do not occur in any attacks and do not occur in some other analysis. So maybe you will try to think if it is the problem of the multi-instance game technique itself. For example, it will introduce this somewhat strange parameter. And also, is it that we haven't utilized the full potential of multi-instance games, and can we prove potentially better bounds? And our first result shows that indeed for b equals to 1, we can utilize the multi-instance games technique more thoroughly to prove an almost tight bound. And we also simplified the proof for b equals to 2, although we didn't give better bounds, but there's almost everything we can do. So our next result states that why is it the case? Actually, we have already found the corresponding attacks for the multi-instance games such that the given bounds matches the current upper bounds we have proved by multi-instance games. So it generally means that if we want to continue to shorten the gaps between the upper bounds and lower bounds, probably we shouldn't rely on this multi-instance games technique. Okay, we have been talking about MI for a long time. Let's go into more details about them. So the reason why we would like to use multi-instance games is that we have this good theorem states that we can reduce an auxiliary input adversary with some success probability to epsilon to a multi-instance game adversary with probability epsilon to the s. So the idea is simple, is that you already have an AI adversary, but you do not know the advice piece, so you can just guess it. You have 2 to the minus s probability to guess it correct. And if you guess it correct, you can have the winning probability epsilon almost in each round. So we can, the probability will just be amortized into this exponential factor. And more precisely, what multi-instance game does is also very similar to the random oracle model. For example, it has of many stages. At the beginning of each stage, it receives a challenge, and it can make T queries to the oracle, and it need to output the, say here, the collision. And here's the general picture that is for round 1, round 2 until round S. He will receive as challenge thoughts, and he will need to give different as different outputs. And the oracle will check if this collision are indeed valid. And something to notice here is that it is very different to auxiliary inputs, that there's no longer the advice string. At the beginning of the first round, actually the adversary knows nothing about the function, and he need to answer and prepare correctly. But one thing different here is that the function f will not change in different rounds. So, and my adversary, what it can do is that it can utilize the information it has in the previous rounds. For example, in round I, he will already make, say, I-1 times t queries to the function f, and he may already have some idea of what this function looks like. And he can indeed use this function's properties to help him design, to help him find collisions in the current rounds. Although he need to win S rounds to win the whole game, it is still possible for us to find some interesting things here. And the main idea for proving lower bounds via multi-instance techniques is we are trying to bound the success probability of the multi-instance. And if we can do this, according to the previous theorem, we can just transform it to a corresponding upper bounds in the original AI adversary. And there are reasons why we'd like to use MI, because there's no advanced Bs, and we can use many good techniques here, and it is often easier. So let's come back to our results again. So for B equals to 1, we examined the multi-instance technique more carefully, and combined with compression argument, we get an almost closed bound. Here, almost closed is that there's a similar gap between the function inversion that has this form of gap. So maybe it is hard to further close the gap. And we will not go into details, but the more interesting thing is that we already have some matching attacks in multi-instance games. For example, for B equals to 2, I mentioned that there's a strange S squared T force to the C squared term. And we already have find attack that has this specific winning probability in the multi-instance setting. So it just means that this is an inherent problem of the multi-instance technique itself, and probably we cannot use them to further bridge the gaps. To introduce this attack, we'll first come back a formal definition of the sponge functions. So we have mentioned that it is a permutation from R times to C to R times to C. Here, R is actually the domain of our message, and C is our domain of the random source, or the so-called initialization vector. And we repeat B times to get a function. And what we are trying to do is that we are trying to find a collision in the multi-instance setting. And you can imagine of how can we find the collision is that we will try to start at a source and find 2 different passes. Here, when B equals to 2 means we only have 2 length passes, such that they will try to finally collide at some point. For example, if they share the same thing 0 here. So one thing we can hope to do is that, recall that we have the inverse oracle here. We may try to use this inverse oracle to carry out many different thoughts that will finally collide at 0. For example, we will constantly query f-1, 0i, and we will get different things like m1, c1, m2, c2, something very different. And this is the first half. And for the second half, for example, when we are given this challenge thought A, we will try to query different messages starting from these thoughts. And we're hoping that what if we can hit some previous thoughts that we have made before in the step 1. So what does it mean? If we can indeed hit a thought here, that is, we can have 4 queries of this form. The first query and the third query is what we have occurred in the step 1, and the second and the fourth are the queries in step 2. And if they can share the same sort A1, and it means we can design the messages properly in this way. That is to say, because we know they share the same message, share the same sort, we can design the message such that it just will go through the edges. In the previous one, we used the edges f-1, but here we will try to go through it from the positive way, such that the messages will indeed collide at the same sort. And you can have a check that if we have this thing, indeed, we can perform a valid collision in this way. And a short notice is that we can guarantee that we will meet enough number of different sorts, and the probability of hitting such two sorts will be large enough. And this is the general idea for the finding the attack. And here's some other attacks. So finally, for a recap, we have showed better bounds for b equals to 1 in finding collisions in the auxiliary input model. And we have showed that there are limitations of the current multi-instance technique. So it's interesting if we can have tighter bounds, or if we can find better methods, or even if we can find better attacks to close the gap. Thank you.
Questions? Then maybe I have one question about the kind of the difference between the security of sponge constructions and Merkle-Darmstadt constructions. Somehow in the beginning I was thinking, does this mean we should move back to using Merkle-Darmstadt hash functions in practice, or what does this mean? Because you emphasized the inverse oracle multiple times. I think, maybe we can elaborate.
Because it shows that in the auxiliary input model, maybe sponge functions are less secure, but actually in many cases, the adversary do not have this specific power like auxiliary input. So in general use, it should be okay, but in this specific scenario, it may have some problems.
Thank you. Questions? All right, then let's thank Rachi again. All right. So we now return to communication lower bounds, this time in the context of continuous group key exchange, and Miguel Gueto Noval is going to give the talk.
Hi, everybody. So I'm going to be presenting this paper recently presented about on the topic of post-compromise security and the upload costs of getting this notion of security for protocols for continuous concurrent continuous group key agreement. So basically, let me start by motivating and contextualizing this paper. So basically, we're talking about group messaging, which is something that we are, for most of us, and actually billions of people around the world are familiar with, since this is offered by very popular apps like WhatsApp or Signal and many others. Communication in this context has an asynchronous nature because users may be offline, then maybe a few hours later, they come back online. And also there is another property that's important to consider, is that these groups may remain active for a very long period of time. So here we have picture 6 users that we're actually interested in the case of very large groups, end users. And here each user basically communicates with the server. So it uploads and downloads some messages from this server. And we're actually going to distinguish between two kinds of messages. The first ones are the ones users actually want to send. So hi, maybe a picture, video. Then there is another kind of message, which is the messages that are used to actually provide security to the users. And we basically want to study the upload cost, so how many messages have to be uploaded to the server in order to provide some notion of security to these users. More specifically, I'm going to be considering a primitive called continuous group key agreement, which basically supports group messaging by giving the users a way of agreeing on a key, maintaining this key over a long period of time, and it does so on a round-based way. So in every round, users agree on one key, and then they just use this key to send the messages I was talking about before. So a picture or a video, whatever they want to say. And then, as you can see here at the bottom, we have 3 on the left. So we have for users, it's KI denotes a pair of public and secret keys. Users know the keys along their path, or at least the secret keys. Of course, they can know more public keys. And then it provides the possibility of doing updates. Here on the right, Alice is doing an update, changes the keys along her path, and just tells Bob, this is the new K5, and it tells Charlie and David by encrypting the new K7 under key K6. Oh, hey, this is a new group and the new key that we all agree on, and we're going to be using in this round. So, of course, it's a cryptography conference, so I'm going to be talking about security as well. So here there is an adversary that is giving the possibility of corrupting users in every round. And the property we want is post-compromise security, which basically says if all corrupted parties have done sufficiently many updates since they were corrupted, we must have a new secure key. And the topic, so the last word in the title that I haven't really talked about is concurrency. And the question is, okay, in the previous picture, only Alice was doing an update, but what happens when we have several parties doing updates? Maybe actually even all users in the group. So here I have 2 different protocols that are like the 2 approaches to dealing with concurrency. The first one called proposing commit and used in a standard recently introduced by the IETF called TRICM. And the second one is COCO. So what has happened in the first picture in both cases, in which all nodes are red, is that the adversary has corrupted every single party. So right now, the adversary knows every single key in the string. And then the subsequent pictures represent the next few rounds in which every single party is doing an update. And these updates are being done concurrently. So we see how the trees heal. And in the first case, after just 2 rounds, the key at the top is no longer in red. So it's a secure key. So it has achieved 2 PCAs. So security after just 2 rounds of updates, but it has done so at a high cost, actually n squared, because what happens in the last round is that party Alice has sampled a new path and then has encrypted the nodes along her path to the other parties. And if you actually look at the number of edges that reach one of the trees along Alice's path, there is a linear number of those edges. So basically, if this is done by all users, it has a cost of n squared. While if we look at what COCO does, COCO basically what happens that every user is doing just sampling the path, a new set of keys for their path, and sending this to its neighbors basically. So the go path, which means only a logarithmic number of ciphertexts is used, and it does so. And as a result, it requires more rounds to heal a logarithmic number of rounds because these are binary trees, and this is being done by all users. So we get a cost of n times log square n. So lower cost, but more rounds. So as I've just said, proposing commit has a worst case total update cost. So the cost of all users together of n squared. And actually, we know this is optimal because in 2020, Beanstalk, Todis, and Resla gave a lower bounding sum symbolic model that shows in the worst case, this is the best you can get. So we know it's optimal. And as I've said, in Cocoa, it was proven by giving a protocol that with more rounds, you can lower the cost. So the question we study in this paper is basically, well, can we get lower bounds for the case of this kind of delay notion of PCS, which we call KPCS, in case just the number of rounds you're willing to wait until you get security. And we also give upper bounds that are very close to this lower bound. And this applies to any protocol basically as constructing from public encryption and pseudo-random functions. So as I said before, there was this symbolic model used by Beanstalk, Douglas, and Reza. We also use it though for fewer cryptographic primitives. And in order to prove lower bounds there, what we do is translate that problem into a combinatorial problem. So on the left, I'm drawing a protocol basically. So the actual keys are there. On the right, I'm going to be drawing the combinatorial problem that we actually studied. So, here all keys are safe, the adversary doesn't know anything. So we just put on the right a set associated to each of these keys that consists of the users who know the corresponding key. So in this combinatorial model, we have this set system that should correspond to the safe keys. We have a sequence of updates and a sequence of corruptions. Here, Alice was corrupted. So we just remove the sets that contain Alice from the set system. So the first picture captures correctness because there is a shared key, which is represented by the set of all parties being part of the set system. In this second row, we are saying this is actually the set system of secure keys because there are no sets that contain corrupted parties. And then in order to study communication cost, we must make sure there is a connection between the number of messages that are sent on the left when doing an update and something related to these sets. So we basically have Alice doing an update. This means the keys Alice knew, the new keys are now secure. So they're back in the set system here. In the set system here. Okay, thank you very much. And now we must make sure there is indeed this connection I was telling you about. So we do so by looking, for instance, at the set here ABCD. And I'm not sure if you can know this, but it's written as a union of three sets. The first one is color in blue, which is a singleton that just contains Alice, which was a new key, just sampled by Alice. And then there are two more sets, singleton B and the set that consists of two parties C and D, which were already part of the set system. So we basically say, okay, Alice, here on the left, sent to ciphertext, which correspond to the dash edges. On the left, encryptions to K2 and the key K6. And those are exactly the black, the sets color in black here on the right. So that's the notion of cost we are basically considering here, which indeed corresponds to counting ciphertext, which is exactly what Alice is going to be uploading, and therefore what we are actually studying. Now I'm going to present to you the lower bound. So first, let me give you an idea of what's going to happen. So we start at time 0. So this is a timeline. The first round is just a setup. Then in the middle, there is going to be a round of corruptions. And then at the end, we want a secure key again. So what we say is no matter, so there is this kind of first, oh, sorry, I'm doing something incorrectly, I think. So there is this kind of get ready phase. So you can choose any sequence of updates before the corruption takes place. Maybe one that you think is very good to lower the cost in the future. Then what we say is, okay, there is still a way of finding a set of corrupted parties in this round here that corresponds to the vertical bar colored in red, and a sequence of updates for slightly more than K rounds that will make you have a total update cost of at least k times n times k root of n over log n. So now let's look at the statement slightly more formal. For the exact bound, which here does not include an epsilon, that is actually part of the actual statement of the formal one, which you can find online. So basically, we consider a small epsilon, and we're going to ask for security after slightly more than k many rounds, so 1 plus epsilon times k, and we give you this time to get ready. No matter how you do it, we are going to give you a set of corruptions and a sequence of updates that satisfies that every corrupted party will have done at least k many updates, and therefore you must make sure the key is secure, and the total cost over these healing rounds is going to be at least this expression here. And we also give a translation theorem that takes this bound in a combinatorial setting and gives you a bound in the symbolic model for any scheme that is correct, and keep KPCN secure and build only from public encryption and theorems. Finally, let's compare this to the existing upper bounds. So before we had already said that n squared was optimal for 2 rounds. These were basically for k equals 2 matches that. And we also give a product called Coco Light, and it's just slight variation of Coco that is up to log n factor matches the bound, the lower bound we got. So it's very close to the lower one we just talked about. It leaves the open question of whether we can overcome this bound by considering more powerful primitives, or maybe not asking for perfect correctness. Thank you.
Questions? Can you explain where your proof doesn't work anymore if you allow, say, dual PRFs?
Yes. So what happens is that basically, when we look at the picture here at the bottom, we are always talking about the cost of one specific round, and using dual PRFs or some other primitive, maybe you can delay this cost over several rounds. So basically, the ciphertext is sent in 1 round, but it doesn't really correspond to when the user learns the corresponding secret. So that's where the translation between symbolic and combinatorial, at least this combinatorial model, kind of works.
Thanks. Any other questions? Okay, then let's thank Miguel again.
Okay, can you see my slides and my screen?
Yes, we can see your slides and your screen. Excellent. Okay. Then, the next talk is about new lower bounds and new lower bound techniques and relation between new lower bounds in the generic group model. And Charlotte Hoffmann is going to give the talk.
All right, thanks. Yeah, so this is about our paper, Generic Group Lower Bounds via Reductions Between Geometric Search Problems. And this is joint work with Benedict and Guillermo. So when we consider the hardness of assumption, sorry, 1 second. When we consider the hardness of assumptions and groups, we usually consider the setting where we have some problem in a group G, and then an adversary that gets as input the description of the group. And it also gets as input some instance, for example, a group element here, and it needs to produce an output. So in this example, this would be the discrete log of the group element. Okay, and now cryptographic schemes, they rely on certain assumptions that problems like this are hard, but in the standard model, there's no way of proving that this actually holds. So if we want to find some evidence of hardness for those problems, we need to move to idealized models. And one example of such an idealized model is the generic group model. So here we restrict the access of the adversary to the group. It does not get the description of the group as input, but there's an oracle that knows the group, and the adversary can interact with this oracle. One example is Shoup's generic group model. So here the oracle has a random labeling function L that assigns a label to every group element. And then the adversary only ever sees labels of group elements. And when it wants to perform a group operation, it sends the labels of two group elements, for example, here A and B, and then the oracle responds with a label of the addition or the multiplication of those group elements. Another example is Mauer's generic group model. Here there's no labeling function and no labels, and the adversary just has abstract handles to interact with the group. And now in those generic group models, we are actually able to prove hardness lower bounds. Because what we've just seen is that all the adversary can do is send queries to this oracle, and so we can count the number of queries that the adversary makes. And this way, we're able to prove lower bounds on group operations required to solve a problem. Shoup's GGM can also be extended to allow for pre-processing bounds. So this means we have some first adversary, which is unbounded, and it gets as input the entire description of the labeling function L. Then it can perform some unbounded computation and then send a bounded advice string to a second adversary. And then the second adversary is now bounded, and it obtains the instance of the problem, and it can start trying to solve the problem. This is a more realistic model because in practice, most crypto systems, they rely on a few standardized groups. So it's actually quite possible that an adversary can perform pre-processing on them. What we can also do in those models is we can transfer lower bounds between problems via reductions. And one way of doing this is to use the algebraic group model. So this is another idealized model where the adversary does see the description of the group, and it does get as input a real group elements. However, whenever the adversary outputs a group element, then it also needs to output some explanation of how it has derived this group element from the elements it has seen so far in the transcript. So in this case, this would be a vector of coefficients, alpha, beta, gamma, and then it needs to prove that the exponent of its group element is a linear combination of the exponents of the group elements it has seen so far. Okay, in this idealized model, we cannot prove lower bounds, but we can prove reductions between problems. And now if you want to transfer a lower bound in the GGM, you could try doing this. So you start with a problem A, for which you already know a GGM lower bound. And then to transfer this problem to problem B, you could try to find reduction against an algebraic adversary from problem A to problem B. Okay, this approach is nice because the reductions are so simple. You don't have any labels or any oracles that you need to take care of. However, if you want this approach to work, so if you want to this algebraic reduction to carry over this GGM lower bound, then you need to assume that any generic adversary is also algebraic. And this is only formally proven in Mauer's GGM. And in Shoup's GGM, it does not hold in general. Another downside of this approach is that it's not compatible with pre-processing bounds. And now what we do in our paper is we present a new technique to transfer GGM lower bounds, which is usable in Shoup's GGM, and it's compatible with pre-processing bounds. All right, let's take a look at the technical overview. So we consider reductions via geometric search problems. So we're in the same setting. We have two problems in the GGM, problem A and problem B. And then so far, I've always said, okay, we already have some lower bound for problem A. But how do you actually obtain this lower bound? Well, there are different ways. You could try to prove it in the GGM directly. But another popular approach is to first define a geometric variant of problem A, and then a reduction from the geometric problem to the problem A in the GGM. And then for this geometric problem, you can compute an information theoretic lower bound. Okay, so we have this lower bound for problem A, and now we want to transfer it to problem B. And the approach that we've just seen was this. You find a reduction from problem A to problem B using an algebraic adversary. Okay, in our paper, we went into a different direction. So we observed that you can also do this. You can also define a geometric version of problem B, and then find a standard reduction from geoproblem A to geoproblem B. So this means if you go this route, you also transfer the lower bound, but you don't need an algebraic adversary. And because you can get rid of this algebraic adversary, you can also move from the plain GGM to the bit fixing GGM. So that's the GGM that allows for proving preprocessing bounds. Okay, but in the rest of the technical overview, we're just going to consider the plain GGM for simplicity, and we're going to look at a specific example. So we want to now prove a lower bound for a CDH in the GGM using a lower bound for the geometric discrete log problem. And the first thing we're going to look at is this arrow right here. So we need to define a geometric version of CDH, and then we need to find a reduction. Okay, let's start with the definition of the problem. So we have a challenger and an adversary, and the challenger samples two elements from a field of prime order. And we will view those elements as coordinates of some point P in this coordinate system on the left. Now, what the adversary is allowed to do is it can query lines, and it asks if the point P lies on the line. In this case, it does not, so the challenger replies with 0. Now the adversary tries again, the point is still not on the line, so the challenger replies with 0 again. And now here in this query, the adversary has queried a line which contains the point P, and so the challenger answers with yes. Okay, so in prior works, when people looked at those geometric problems, they usually considered discrete log type problems. So there, the adversary really needs to find the point P. But here in this case, in a CDH type problem, the winning condition looks a bit different. So what the adversary needs to do, it needs to output a linear combination of x, y, and 1, such that when you take the target polynomial, which in the CDH case is x times y, and you subtract the output of the adversary, then this defines a polynomial. And you can see the 0 set of the polynomial on the left in the coordinate system in blue. And then we say that the adversary wins if and only if P is contained in the 0 set. And that's the game. And then in the paper, we show this reduction from the GeoCDH problem to the CDH problem in the GGM. And to give some intuition, so the reduction wants to use this generic adversary that plays the CDH game. And so it needs to simulate the GGM oracle. And it can do this using those line queries to the challenger to do this consistently. And then in the end, the generic adversary will output a label of the element G to the XY. And this label corresponds to this linear combination that we need to send to the challenger. Okay, this is very high level, and it looks a bit complicated right now, maybe, but you get used to it pretty quickly. And also, this is just a very specific example. So what we do in the paper is we look at a much more general problem. So we define a geometric versions of what we call a multi-instance Uber problem, which is a very general problem and more general than other Uber problems in the literature. And then we prove an analogous lemma to the one below, and we prove it in the GGM and also in the bit fixing GGM, which is the one that allows for preprocessing. Okay, and we try to define this problem as general as possible, such that when you make use this technique in future work, then probably or hopefully your problem will already be covered by your Uber problem, so you don't need to do this step again, and you can use our reduction in future work. Okay, so that's what's happening here in this arrow, and now we're going to talk about the other one. So we also need to find reductions between two geometric problems. And when we tried to do this, we've made this observation that many AGM reductions actually have a very natural analog for geometric problems, which is nice, right? Because the upside of the AGM reductions are that they are super simple. And it turns out that the reductions between the geometric problems are similar. So I don't want to go into the details, but what we do in the paper is we do the reductions for some examples. So we show a reduction between geometric versions of the Q-strong D-log to the Uber problem, which is similar to the AGM reduction that already exists in the literature. And then we also go through some other examples. Yeah, if you want to know what these problems are, just check out the paper. Okay, so that's what's happening here. And this concludes the overview of our technique. So to sum up, what we do in our work is we present a new technique to transfer lower bounds in the GGM. And we give new pre-processing lower bounds for several problems. What are the interesting open problems? Well, first, it would be nice to adapt the technique for decisional problems. In our paper, we just look at computational problems because we don't know how to define geometric versions of decisional problems, but it doesn't seem out of reach. So this would be something cool to look at. And the other one is to extend the bit fixing GGM to allow for decisional oracles and to work in bilinear groups. So yeah, because once you have this, then you can also use our technique as is, and it will also give you pre-processing lower bounds. So the only thing that's preventing you right now is because the bit fixing GGM needs to yeah, be extended to decisional oracles and bilinear groups. And that's it. Now I'm happy to take questions.
Yes, anyone has a question? Then maybe can you say a little bit about the difficulty of using this kind of geometric approach to study decisional problems?
Okay, let's see. Yeah, so I guess we tried for a while. Let's go back to the problem. Okay, so let's see, what would happen if we would want to define a decisional version of this? We somehow, yeah, the thing is in those geometric problems, you can see that the adversary does not even get an input, right? It's just, it knows that there's some point there and they can query the system. So let's see, right now I wouldn't even know how to, yeah, what the challenge for the adversary would be. But to be honest, it was a while ago that we thought about it, so I don't really remember the challenges.
Thank you. Any other question?
Following up to this question, there is a paper about an algebraic version of AGM. Maybe that the technique in that paper can be used to also define decisional version of a geometric problem. I don't know if you're familiar with that paper.
So wait, that's the paper about, yeah, decisional problems in the AGM, right?
Yes.
Yes, yeah, I'm familiar with the paper, yeah, but I mean, maybe it's possible. I don't think it's impossible, but we don't know how to do it. But yeah, thanks.
Okay.
All right, then let's thank Charlotte again.
Thank you.
All right, and the last talk in the session studies oracle separations for extremely lossy functions, and Felix Rohrbach is going to give the talk.
Thank you for the nice introduction, and this is joint work with Mark Fischling. So yeah, I'm going to talk about extremely lossy functions, or short ELFs, which are families of functions defined by Mark's entry that either exist in injective mode or in an extremely lossy mode. So in injective mode, every image has at most one free image, while in the extremely lossy mode, the whole size of the image is at most polynomial. The mode is defined via a public key, which is either generated in injective or in lossy mode. And further, we want that these two modes are computationally indistinguishable. Now, elves are interesting because they can be used to replace random oracle model assumptions. So there have many attempts to replace random oracle model assumptions because it's not the same as the standard model, including correlation intractability, universal computational extractors. And extremely lossy functions is a new candidate here, which has the upside of only needing standard-ish assumptions and already being useful for quite many applications. So to construct ALF, Zentry used the exponential decisional k-linear assumption, which is a generalized version of the exponential decisional Diffie-Hellman assumption. And he claims that these are probably true for example, elliptic curves. However, one question is whether we really need public key cryptography to build ALFs. So already Zentry was wondering whether maybe exponentially secure one-way functions or collision-resistant hash functions might be enough. And there has been a paper by Holmgren and Lombardi who introduced a primitive called one-way product functions. And also they were wondering whether they could build ALFs from this. So this motivates our main research question: what are the minimal assumptions for building these ALFs? We have two negative results here. So the first one is that there cannot exist a fully black box construction of ALFs from exponentially one-way functions, exponentially secure collision-resistant hash functions, one-way product functions, and many more. Indeed, anything that exists relative to a random oracle. We call that set oracle crypt in a nod to mini crypt, which is everything you can build from a one-way function. And actually, this turns out to be true even for just moderately lossy functions. So moderately lossy functions are functions that have in lossy mode an exponential size, but are at least compressing by 1 bit. On the other hand, we show that ALFs itself are also not enough to build a public key cryptography or key agreement, especially from it. So it seems to be that our standard symmetric primitives are not enough to build extremely lossy functions from, but it's also not necessarily something that belongs to the public key cryptography sphere. So I'll first talk a bit about our first result here. For that, we use an oracle separation, as Chris already mentioned. So we build a random oracle and a piece-based type oracle relative to which all these oracle primitives exist, but lossy functions and ALFs do not. And let me note that we use an idea from Piaczak, Rosen, and Seeger from TCC 2012 here. So the idea is as follows. So I'll first give you a very inefficient distinguisher. So if we look at the image size of the function relative to our random oracle, if it's in injective mode, clearly the function size has to be 2 to the n. While if we are in lossy mode, the image size of the function is at most half of that. So if we now introduce a distinguisher that just queries the function on each input, does all the queries to the random oracle, and thereby computes the image size of the function, and then decides whether the function is injective or lossy based on whether its image size is bigger than 3/4 of 2 to the n or less, then we clearly have a distinguisher. However, this distinguisher needs to do exponentially many queries to the random oracle, and therefore surely cannot be efficient. However, it turns out that we actually don't need to query everything to the random oracle. Only the heavy queries are important for us. So query is heavy if it appears in f of x for at least a polynomial fraction of all x. I'll now explain why these heavy queries are important. And for that, first note that we want our hardness of the distinguishing between injective and lossy mode to be somehow dependent on our random oracle, because that's our source of hardness. So if we have some function that is injective for some random oracle O here. So for these two inputs, we have different outputs. Then we want that for a different random oracle O prime, the function is lossy. So for example, here we could have a collision between x1 and x2. Further, we need some observations about extremely lossy functions. And the first one is that lossiness is very much a global property, in the sense of if you go from an injective function to a lossy function, you need to change on average at least every second output, because now on average on every second output, you need to have a collision. And the other one is that the key generator that generates the public key either in injective or lossy mode itself has to be efficient and therefore only knows the random oracle at polynomially many positions. And therefore the other positions can't really influence the mode because the generator has to always give out an injective or a lossy function, or at least with overwhelming probability. So yeah. Let me go back to my previous picture. So if we now have to change at least half of the inputs of X from injective to lossy, then at half of the inputs X, we need to have some or multiple queries to the random oracle that define whether we have a collision there or not. However, now our key generator only knows about polynomially many of these queues. So it has to reuse some of these queues over and over again, and thereby these queues become heavy queries. Now, it's very nice that heavy queries are actually quite easy to find. So what you do is you just query random inputs to F, see which queries F does to the random oracle, and collect all these queries in the set QH. And this QH, if you do it a polynomial number of time, of course, has polynomial size because F itself always does polynomially many queries to the random oracle. And because, yeah, we do that polynomially many times. But also with overwhelming probability, we know that all these queries, all the heavy queries are now contained in QH. Now with that, we can actually build an efficient distinguisher. We start again with our inefficient distinguisher. But now we only query all the queries in QH, which hopefully contains all heavy queries, to the original random oracle, and everything else we just sample new. So we basically have a new random oracle here, O prime, which only is the same on with the original oracle on the elements of QH. Now, of course, if we now replace the original random oracle with our new oracle, the image size of the function might change. But we can argue that because basically the lossy function has to use these heavy queries, these non-heavy queries will only change the image size very slightly. And therefore, our distinguisher still decides correctly. That concludes our oracle separations, which now show that we cannot have a fully black box construction of ELF from anything in Oracle crypt. And now also say a little bit about our second result. So there we want to show that we cannot build public key cryptography or key agreement from extremely lossy functions. And for this, we use the well-known result by Impact, Diaz, and Rulich that no key agreement can exist relative to a random permutation. Now what we do is we start by constructing an inefficient ELF oracle, which contains of a generator for the public key and an evaluation oracle, which both have access to a random permutation pi. And for these, we prove a simulation lemma, which says that there exists some efficient algorithm wrap with access to the random permutation, such that access to this algorithm wrap or to the ELF oracle is indistinguishable. And we note that this wrap algorithm doesn't need any global state. Now, we start by assuming that key agreement exists relative to our ELF oracle. So there exist Alice and Bob, and they speak with each other and the ELF oracle and agree on some key. Now, due to our simulation lemma, if we introduce our wrap algorithm here, this cannot change, it cannot break completeness of the key agreement, because otherwise we would have an efficient distinguisher against our simulation error. Now, however, because RAP is efficient, we can see this as two parties that just relative to random permutation agree on a key. So we know that there exists the Impagliazzi-Rudy adversary. And now on the last step, we again remove the RAP protocol, which we can again do again, because otherwise we would have an efficient distinguisher. And so now we have an efficient adversary against our original protocol, and therefore a contradiction. So to conclude, we have shown that no fully black box construction of elves from anything in Oracle can exist. But on the other hand, also that no fully black box construction of key agreement can exist from extremely lossy functions. So this leaves open what we actually need to use for extremely lossy functions. And I think this is quite interesting future work. And yeah, thank you. And I'm happy to take questions.
Questions? And then, we know how to build elves from exponential DDH, and now we know one-way functions are not enough. Do you think generic public key encryption is enough, or what's your, I don't know, or like, do we know elves from IO, or maybe IO is not enough? What is your, I don't know.
We don't really have any constructions, as far as I know, except for the Sentry constructions. So I'm actually not sure whether you can build it from public key encryption, generic public key encryption directly. So yeah, it's still there's nothing known. It would be really nice to have more constructions of extremely lossy functions. So yeah.
Or more lower bounds, but
yes, sure.
Yeah.
Do you need all the power of p-space for your separation, or what's the like lowest complexity oracle you can use?
Well, actually, we need a bit more than p-space. So this is why there was some p-space plus, because we also need to sample a new random oracle, which is kind of hard in p-space. So we actually need a bit more than p-space. I'm not sure whether we can remove anything from p-space. Maybe.
Thank you.
Thank you for the question.
Okay, so according to my understanding, your results holds for moderately lossy function, right? Not so that do you in any place use the extreme region?
I mean, yes, our first result totally holds for, so we basically prove for lossy functions, because lossy functions are less strong than extremely lossy functions. But for our second result, it becomes a bit more complicated, because there, if you start with a stronger result, the difference is a bit harder.
All right, then let's thank Felix again.